In the world of metabolomics, one of the most critical challenges is identifying unknown small molecules from tandem mass spectrometry data, a technique that fragments molecules and measures their fragment ions to produce complex spectral patterns. But here's the catch: these spectra don't come with molecular labels. So how do we go from a mass spectrum to the actual chemical structure behind it? The standard approach: use deep learning to predict a molecular fingerprint, a binary vector encoding the presence or absence of specific substructures, and then search a chemical database for the best match. That sounds straightforward. But here's where things get interesting. The loss function you choose during training fundamentally shapes what your model learns and what it fails to learn. In this video, we'll uncover a profound and underappreciated trade-off in modern computational metabolomics. Optimizing for accurate fingerprint predictions often hurts molecular retrieval performance, and vice versa. And we'll explain why, using both empirical evidence and novel theoretical analysis. Let's break down the two objectives that are often conflated, but are actually in conflict. First, you want your predicted fingerprint to be similar to the true molecule's fingerprint, measured by metrics like Tanimoto similarity, also known as Jaccard index or IOU. This is about prediction accuracy. Second, you want the model to retrieve the correct molecule from a candidate set, typically defined by equal mass or equal molecular formula. This is evaluated using hit rate at K, which measures whether the true molecule appears in the top K most similar candidates. Now, here's the paradox. The model that predicts the most accurate fingerprint isn't necessarily the one that retrieves the right molecule best. We tested this systematically on the MassSpecGym benchmark, a large-scale dataset with over 230,000 spectra and 28,000 unique molecules. We trained 8 different models, each using a different loss function. Bitwise losses, binary cross-entropy BCE, focal loss, optimize each bit independently. Vector-wise losses, cosine similarity, IOU loss, optimize the full fingerprint vector. Listwise losses, contrastive losses, compare the spectrum directly to candidate fingerprints in a ranking setup. The results: a clear Pareto front emerged. The models that maximized Tanimoto similarity, like the IOU loss, achieved the best fingerprint accuracy, but the worst retrieval performance. Meanwhile, models trained with contrastive losses, especially those using cosine similarity on embedded representations, delivered the highest hit rates, but their predicted fingerprints were less similar to the ground truth. So optimizing for one goal actively undermines the other. To understand why, we need to shift perspective, not from the loss function itself, but from the decision rule it induces. In machine learning, we don't just minimize loss, we decide what to output. And different objectives lead to different optimal decisions. Let's consider a simple example. Suppose you have a spectrum and 4 candidate molecules. The true molecule is the most likely, but the others are close in structure. Some are very similar, others are quite different. Maximizing Tanimoto similarity might push the model to predict a fingerprint that averages across all candidates, a kind of compromise vector. Maximizing hit rate at 1, i.e., getting the top candidate right, pushes the model to amplify differences to make the true molecule stand out. But here's the key insight. The Bayes' optimal decision depends on the structure of the candidate set. We formalized this using a regret analysis, a measure of how much worse your decision is compared to the ideal one. Our theoretical results show that the regret, the performance gap between optimal decisions under different metrics, depends on 2 things. 1, the conditional probability distribution over candidates, how uncertain the model is about the true molecule. 2, the similarity band of the candidate set, specifically, the difference between the minimum and maximum similarity between the true molecule and its candidates. If your candidate set contains molecules that are very similar to the true one, even duplicates, then maximizing similarity becomes dangerous. The model might predict a fingerprint that's in the middle, which scores well on similarity, but fails to distinguish the true molecule. Conversely, if the candidates are widely dissimilar, then maximizing similarity can help retrieval, but only if the true molecule is clearly the most similar. So the trade-off isn't arbitrary. It's driven by the data structure, and it's quantifiable. So what should you do? If your goal is molecular retrieval, which it usually is, then use a listwise contrastive loss. These directly optimize for ranking the correct molecule at the top. In fact, our results show that even a small weight on a contrastive term, combined with a similarity loss, dramatically boosts retrieval performance. But here's a deeper implication. The choice of fingerprint matters just as much as the loss function. We tested 5 different fingerprint types, Morgan R equals 2 to 8, RD-KIT, and MAP4, and found that MAP4 fingerprints have a more favorable similarity band distribution. Lower maximum similarity, narrower bands, fewer near duplicates. And when we trained models on these fingerprints, the gap between retrieval and fingerprint accuracy was significantly smaller. In other words, a better fingerprint representation reduces regret, meaning that improving fingerprint similarity does help retrieval. This suggests that MAP4 could be a superior alternative to the traditional Morgan fingerprint, especially for retrieval tasks. This trade-off isn't unique to mass spectrometry. It arises whenever you use binary representations for similarity-based retrieval, from item recommendation to image hashing. The core lesson: don't optimize for the wrong metric. If your ultimate goal is retrieval, don't train your model to maximize Tanimoto similarity. Train it to rank correctly. And don't assume that better fingerprint prediction leads to better results. Sometimes, a less accurate but more discriminative prediction is better. This work reveals a fundamental tension in modern AI for chemistry, the gap between prediction accuracy and real-world utility. We've shown that fingerprint similarity and retrieval are not aligned objectives. The optimal model depends on the task. Theoretical tools like regret analysis can guide model design. Fingerprint selection is not just a technical choice, it's a strategic one. As the field moves toward more complex models, from transformers to diffusion generative networks, this insight becomes even more critical. Because in the end, the best model isn't the one that predicts the fingerprint best. It's the one that finds the right molecule. And that means we need to rethink how we train, evaluate, and deploy these models. So the next time you're building a molecular retrieval system, ask yourself, what am I really optimizing for? Because the answer might surprise you.